Thank you for the introduction. My name is Malthe Linquist. I am, as was said, working as a thermal engineer for Blue World Technologies, and has been working with the COCO simulation for around a year now, in which we tried to implement a model for our reformation process in the fuel cell industry.
Page down, I think.
On keyboard, page down.
On keyboard, it's page down. Yes, it's okay. Page down. I don't understand this interview. Okay. Something is working to change the slide.
Just use the yes. So this is the agenda for the presentation, where I will come on the Blue World Technologies as the company, the physical reformer we tried to simulate, and the unit operation of COCO of the Couscous library, the Python unit operation, and so first of all, Blue World Technologies is an ambitious and visionary developer and manufacturer of the methanol fuel cell. In that industry, we are placed in Aalborg, Denmark, and in all the methanol fuel cell is designed to reduce both fuel consumption, CO2 emission, while also ensuring a long range and a fast refueling. And is used. We are trying to implement it in the stationary generator to get out the combustion engine, and also working on getting into the maritime scheme. Furthermore, the fuel cells of Blue World Technologies are based on the high temperature PEM fuel cell technology with the combined of a methanol reforming process. So let's move on to the physical reformer, which we would like to simulate. So the physical reformer is on the picture there, which is basically a shell and tube heat exchanger, in which we inside all the small tubes, which can be seen here. There are several small tubes in which we have a catalyst pellet, which will help the reformation process of methanol and water, steam. And in the shell side, we have a heating oil flowing to ensure that process will take place. Yes. So basically, the methanol steam forming process consists of the three reactions you see out here, and will also all take place together and will all be accounted for. And as it's an endothermic process set of reactions, we will need to have the heating oil to ensure that the temperature level is right and that the reactions are taking place. So to move on, there were different unit operations which we could use on the Couscous library. The first method we used, or the first model we made, was based on a plug flow reactor, where the plug flow reactor simulates a shell and tube reactor in which you can take into account a catalyst. But for that specific model, the reactor was inverted so that the catalyst was placed in the shell instead of in the tubes. And we could come around that, but that will require a lot of additional work to get it to work like we would have it to. So we tend to another option, which was the fixed conversion reactor. The fixed conversion reactor was required for us to set some conversion rates of the three reactions, but that require additional calculation of those rates and then implementing them. And as the rates are based on temperature, it would require other unit operation to do so. So for our model to be more easily calculated, the conversion, we should make up the model. So in the different talks with the people like Jasper, I made up and I thought that a Python unit operation would be more suitable. And furthermore, the last one is furthermore, the energy of the reaction also needed to be accounted for, as we needed our heating oil and we needed to know how much heating oil we will have to flow through the reactor to keep temperature. So that made us come up with the unit operation from Python, the CAPE-OPEN Python unit operation, because we had some different, we had all different CAPE-OPEN options as MATLAB, Python, Excel, CIPLab, and so on. But Python was the most appealing option in this case due to the fact that we will already have made up a Python model for the reforming process, which only needed some small adjustment to be ready to put into our shell and tube reform. So that was the obvious choice for our case. We could have done it in MATLAB as well, but then it would require a license for MATLAB, which was rather expensive compared to the work I actually needed to use it for. So Python was the obvious choice for us. So the block was integrated, and as we can see here, if we had a plug flow reactor or a conversion rate, thick conversion, it would pretty much look the same. But we would need another Python block, so another one of blocks above to calculate the conversion rates and calculate the energy for the heating system over here. So this block, this Python unit operation, both made it look more simple in the flowsheet, but it's also helped with the accurate results of the energy needed, more accurate or more satisfying results for the energy needed in the heating oil, and for the flow out of the reformer also appeared to be more accurate with respect to test we are driving on a smaller system. That was it. Thanks for your attention. A small presentation.
Thank you very much.